clients like there's no tomorrow.
Hello, welcome everyone. Today we will continue and actually we will finalize our subject of pricing of mortgages. Today is block number 4, where we will start with a Python experiment where we will use the knowledge what we have learned before about pricing of annuities or pricing in general of mortgages and inclusion of a refinancing incentive. So I will present you how to perform a simulation of the stochasticity in the notional. Then we will move to the connection of index amortizing swap to swaptions. This will be particularly important if we talk about hedging of your mortgage portfolio and how to link that to swaptions. Then there is a subject that we didn't discuss too much in this course, but this is also important. So this is another source of risk for a bank. It is a pipeline risk. So the risk associated with the optionality that our clients have once they get the mortgage. And finally, we will summarize, and there will be 3 assignments as homework. I hope you enjoy it. Now is the time for Python experiment. In this experiment, we will collect the knowledge what we have learned in previous lectures about simulation of full white model, simulation of swaps and pricing of swaps given short rate process. We will combine this with materials about incentives and amortizing swaps. So if we go back to the previous slide, here we haven't specified anything about stochasticity of our K, which is driven by this is the new swap rate. So it's a new rate that we are going to compare our old mortgage rate to the swap rate available in the market. So this part we haven't defined yet how we are going to simulate. In this experiment, we assume that the dynamics for the underlying short rate model is going to be driven by the whole white model. And this is, you can go back to previous lectures where I discussed how to simulate short rate and how to use that simulated paths for simulation of a swap. So assuming that we have a short rate model for interest rates, we are able to calculate the dynamics for the swap rate, or we can simulate swap rates. Then the swap rates we will use for this market conditions epsilon. We will plug it in then to the refinancing incentive function. This is this sigmoid function of a S-shaped function. So this is this function which tells us whether the client is rational or irrational. So this is, let's say, our old rate. Actually, this should be epsilon of that, okay? And then we plug it into the function depending on what type of mortgage we have. So in this experiment, we will consider 2 mortgages, of course, bullet mortgage and annuity mortgage. And here then we will evaluate notional. As you can see, this notional, it is becoming stochastic because every element starting from the bottom. So okay, we started from the top. You can see we derive everything this way. However, in the simulation, we have to go from the bottom from epsilon until we go into the pricing equation. But if we look this notional that we have here for the corresponding mortgage, it is stochastic quantity. So in essence, we should also be able to derive the dynamics for n in terms of dynamics, the stochasticity that we have obtained from the short rate model, which is driving the swap rate. So this is kind of interesting. We can also do that. It is, however, much more involved because then we have to really go through the dependencies of all those dependencies we have discussed. And also we have a product here. So that's much more troublesome. And of course, given that this equation here, we even if we have process for n, is not going to really help us, because if we simulated our swap rate, we can just simply substitute this stochastic notional that we derive from these 3 equations. We could just simply substitute for this equation here, and we evaluate average for each individual sum, and then we put them together. So that's basically rather straightforward. Let's go back. So here in this experiment, we will have 2 types of mortgages. So this picture on the left, this figure, it is a bullet mortgage. And then here we have annuity mortgage. The red dotted line represents the rational behavior. So where, depending on time, so this is rational behavior, how our notional profile will behave, or will look like. So in a case here, so we see that in a bullet case, of course, the notional doesn't change, and then we have a jump of our notional to zero, and then we have this irrational function which represents that path. This is actually, you can see this is really interesting shape of these notionals, because those are paths of our notional that we have generated depending on the bullet mortgage. So here you can see, for example, if you're on this path, maybe it's a little bit more difficult to distinguish those paths because all of them, they very look alike. But in the code, in a few minutes, we'll go through this steps, step by step, how those paths can be simulated. So you see, if you're here, this basically would mean that you'll be prepaying quite significant amounts. In this, let's say, if you are irrational, you behave according to the refinancing incentive function. And then, of course, at this point, you have very little to return at the last payment. In this case, this is the case of annuity. You see, although in these two cases, I have chosen the randomness of simulated paths to be the same. So here, this profile looks very much different than here. Of course, here the main difference, of course, that this uncertainty here, this you can say, let's say at the time 15, we have this volatility here and volatility here. This volatility, randomness, the spread at this point is much smaller than one for the bullet option. Of course, that comes from the fact that once we go in time, and then the stochasticity, of course, is very important. And if we prepay or repay our notional, then the impact of prepayments will be significantly limited. This is why this will be this impact of the prepayments and stochasticity. It's much smaller typically than if we would have for the notional, which is the bullet type of mortgage, because there we have this huge notional which is outstanding. So if at some point somebody decides to do prepayments, that has significant, much higher, much bigger impact than if we just look at the annuity type of mortgage with prepayments. So this, from the risk management perspective, this the index amortizing swaps, we will need, let's say, less of them in order to hedge this particular risk. In terms of bullet mortgages, that effect will be much more pronounced. So let's take a look at the Python code. In this Python code, we will use all the knowledge we have gained about simulating of mortgages. So this is bullet and annuity. So those are the codes I have presented you before, except this time I have extended those functions to make this CPI, so the constant prepayment rate, or the incentive, the prepayment rate, to be time dependent, because now we will use it as a time dependent function depending on which part on the path, stochastic path, we are. So, okay, let's go through all the steps. So the first part is something we already have seen. This is for given zero coupon bond curve. So constructed from yield curve, we generate Euler discretized Euler paths for the full white model. So this is, I'm not going to discuss it further. This is discussed previously in lectures. Then we have this, of course, time-dependent theta, which is also covered. This is also for the full white zero coupon bonds. And this is also zero coupon bond. Important part here, we have a swap rate for whole white. In this case, you see that we are iterating. So we have this today's date, we have a start date of a swap, end date of a swap, and then we add all those zero coupon bonds. So here we calculate the accruing, the annuity part of a swap rate, and then we have two zero coupon bonds, and then the swap rate is the output. And here, of course, everything is based on a lambda expression for the zero coupon bond under the full white model. So the input here is the RT. So you see that the stochasticity part. So you remember in a full white case, we have this affinity. This means that every zero coupon bond, it can be defined as the exponent of A plus B times RT. And then this RT would need to be generated from Monte Carlo paths. So this is, I discussed also in previous lectures, but this is important to keep in mind that it's not a swap rate that you would have just simply based on the yield curve. Here we have a swap rate for full white model, and then we have this additional input for RT, and those are the stochastic paths at every time t. Okay, so then this function will return our swap, and then we have here those two mortgage amortization schedules. So these are the profiles here for bullet and annuity for our mortgage payments. And let me take a look here. So you see this CPR or the prepayment rate. It is exactly the same functionality what we have discussed before, except for this time. This time we have this additional indexation with respect to time. So our outstanding notional and how much we prepay would depend where we are on the path, which would depend on, of course, incentive function and the swap rate that we observe in the market. So this time, of course, we have stochasticity in the swap rate. This swap rate is impacting our incentive in the whole lifetime of our mortgage, because we may decide to prepay today, but also we may decide to prepay in the future, depending on Monte Carlo paths for our swap. So then this prepayment, our behavior on prepayment may vary in time. Okay, so of course this is also has to do, so here we are not including our model is rather simplistic. We are just using refinancing incentive is based on single input, which is swap rate. But if you have impact like a burnouts, where client would let's say his dependence, whether he's willing to prepay or not, would depend whether he has prepaid in the past. So that makes it strongly path dependent case. But here, for simplicity reasons, we don't consider that case. And the same extension regarding the CPR and time dependence is also here for the annuity mortgage, where we have this additional indexing for time. Okay, so in the main code, so this is the key block of our functionality of our experiment. So I have defined two incentive functions. So this is a sigmoid function, this is a logistic function, which is irrational behavior incentive of our clients, and the second part is rational. So you see this rational, the incentive is either zero if our epsilon is smaller than zero, and it's 4% if our epsilon is larger than zero. So this is a rational behavior. This is more for illustration of what is the optimal and what is the rational, let's say, boundary condition of our problem. We start with the irrational behavior. Maybe let's start with rational first. So here I'm also using a Python function that you see that's a function holder. So we can just, here this holder I use later in the code here. But at this point we can alternate whether we go to rational or irrational, and then Python will pick up according pointer to the function which we have defined here. Okay, we have a mortgage. Our mortgage that we have got is as 5% interest. This is the mortgage that we will have in our annuity. This is the rate we have to pay. Then this is just a full illustration. I'm also showing you these incentive functions. So this is here deterministic, just a grid of all the of 150 points from minus 10% to 10%, just to illustrate here the incentive functions, whether it is how it behaves with respect to whether we look at the new rate or we look at the epsilon. This is something that we already have seen previously also in this lecture. Okay, so those two first figures are just plotting the incentive function, so this is not so much important. The more important part is the part where we simulate stochastic differential equation, where we simulate swap rate, and we use it to build up our profiles of notional. Okay, so here we have 2000 paths, number of steps is 30. We can later increase that. It doesn't really matter because our mortgage, we assume we will have a 30-year mortgage, so we can also simulate 30 times. We can also increase that. It doesn't really matter. Here are the parameters for the whole white model. So those will need to be calibrated to the market, swaptions or other type of instruments that we are using to simulate those paths. Of course, the calibration of full white model, it is not really covered in this course. I will discuss this later in the follow-up course. Okay, here we define market. So I'm just defining a yield curve, but this is also fixed 5%. Here we simulate Monte Carlo paths from today until the end of our mortgage. And so we have interest rate paths. Here what I'm doing is that for every time step as we go in time, I'm simulating a value of a swap rate. So I'm simulating a swap. And then what I'm doing is that we assume that our client will look at the swap, which will be at the fixed maturity. So we can call it like a constant maturity swap. So it is always client will be always based his decision of the prepaying or not prepaying based on this case on 30-year swap. So you see it's a TI and then I have TN plus TI. So it's always we look at the 30-year swap. In practice, however, you would need to adjust it slightly. So you need to play with those arguments. Also make sure that the function doesn't, because in a swap definition here, you see we divide by this is the annuity factor. So you have to make sure that this is not zero. Otherwise, this will not work. But here, just for illustration reasons, I'm assuming that our client will always look at the 30-year swap. Yes, so in practice, of course, the client will look at the swap that corresponds to his outstanding mortgage. So if you have a mortgage of remaining mortgages, so 5 years, you will not look at 30-year swap because that's part of a yield curve. It's not really influencing your decision. You'll be much more focused on a mortgage of 5 years. So then the swap would be 5 years. But this is a small adjustment you can do. Then if we have the swap rate, the next step is to define our incentive. So you see in here, I'm just plotting the incentive function as a function of stochastic swap rate. So this is, so I'm only looking at the swap rate in 30 years. This is just to show you how this the sigmoid function will look like depending on the stochasticity of a swap rate. Then figure number 4, I will be plotting also the histogram, the distribution of a swap at the end on 30 years. And now we go to the main part where we will use our incentive functions that we have developed, so that we have actually configured here. So we have these 2 incentive functions in order to create the notional schedules. So first, okay, so what I'm doing here, I'm iterating over not time steps. So normally if you talk about Monte Carlo simulation, we always think of time steps. So it's every time step we have a vector of paths. But here, because of the design that is done here about for the annuity and also for bullet, you see that here in those 2 options, those 2 functions, we need to have kind of time dependence in CPR. You see that everything is time dependent. Our schedule, the output of our function here for annuity is a function of gives us the schedule and also profile of notional in time. This means that this doesn't really correspond nicely to the path at given point, but it corresponds more to the time evolution of our paths. For that reason, what I'm doing here, I'm evaluating this incentive function, also notional profile, per path. Because if I'm taking this epsilon, you see at the path number 1, 2, and so on, I get epsilon is a path for the swap rate. So I can see swap evolution over time for one individual path. Then if I have this the first path of ith path for a swap, I have then epsilon, which is also let's say a path realization, because it's only adjusted to a strike. Then evaluate our lambda, which is the incentive function, also is in time. And now if I have this lambda function, so lambda, this incentive function in time, I'm able to evaluate our mortgage profile at every time step from the beginning of the mortgage until the end of the mortgage. In this case, we have a mortgage of 30 years. And then what I'm doing here, I'm storing this in our matrix N. So this will be the main part where we create our stochastic notional depending on an incentive function, stochastic interest rates, and stochastic process for swaps, and also, of course, type of a mortgage that we have used. And here in the figure 6, I'm taking first 50 stochastic paths, and I'm plotting those paths here in this plot. So each path I'm plotting individually, and then we have a no prepayment part. So remember this red line that I have shown you, maybe I mentioned that it was optimal, but actually this is the case where it is no prepayments. So in this graph, where actually we will see in a second, where it's no prepayment and then where the prepayments take place. So okay, let's run. This is the first case. We have a scenario where we have a rational behavior, and here in this code we look at the bullet mortgage. So, okay, so here those are the incentive functions. Here's the stochasticity. So you see there is some randomness for the incentive depending on the stochastic curves. Here's the distribution of our swap rate. This is swap rate distribution in 30 years for swap of 30 years. So we swap observed in 30 years for 30 years from that on. So this will be 60 years from today's. And this is the notional profile that we have for our mortgage. So this is 50 paths, so this is not so easy to see. Let me do 2 paths. Yes, so here it's clearer how those paths behave. So in this case, we have a rather smooth downward prepayment of the notional. We can see it here, and then it's a jump. And then in this case, we did some prepayment in the beginning. Maybe the swap rate was significantly lower, and then we prepaid our notional, and until the end almost, there was no enough. There was no incentive for us or for the client to do any prepayments. And here we had continuously opportunity, or it was always beneficial to do the prepayment. If I run it again, you see now maybe it's more interesting profile. You see there's 2 incentives, they cross. So one, in first case here, we had a scenario where there was incentive initially to prepay, and there was no incentive over time. However, the second path had initially there was nothing, and then it also here was a stagnation. There was the interest rates that we simulated interest rates. They were not in the area that client would do any prepayments. Another one, it's basically slowly, there was in prepayment and client has done prepayment. And at the end, you see the 2 mortgages, they have rather still significant amount of notional to pay. So this is the case where we have a rational behavior, right? So this is the rational behavior. Maybe now let's switch from, from rational, let's do irrational. So this is the sigmoid function. Oh, you see that now it's much different. Yeah? So the profile of our notional payment is significantly different what we have seen before. It's still for 2 paths. Let's make maybe 20. So you see that there is a decaying. So all those paths are much more aligned, that they're going all of those paths, they're going exponentially down, depending on the prepayment rate. Of course, those profiles, they will change depending on the configuration that we have. And of course, the incentive function is a very important one, because you can see that if we have more and more uncertainty in profiles for the notional, this means that we have more uncertainty, more volatility if the stochasticity of the notional that we have to use in hedging process. So then we have to this index amortizing swap or swaption. Later I will show you that we have more impact, and we need to buy or sell more of them to hedge this kind of risk that bank is exposed to. If we increase number of paths, let's say this will be maybe more nicely. Okay, maybe it's too much. It's too crowded. Too many paths there. 100 paths, and then if we increase maybe number of steps, I think number of steps will not really change anything. Let me try. So number of steps, actually it changes depending on it changes the profile. So the swap rate actually becomes, because we do Euler discretization. So this accuracy from Euler, it also, you see, it plays a role. So 50 steps. Yes, actually, so in this setting, we have maybe those number of steps. It is maybe slightly misleading, because here in number of steps, initially I thought that we are only having number of paths, which are more accurate, but actually number of steps also in our simulation would imply where are the moments where client can perform his prepayments. So obviously that would have an impact on the profile of our notional. So the client has more opportunities to perform prepayment, not only on the payment. So here we have a case where we have a yearly mortgages. So if we allow clients to have yearly payment of a mortgage, but prepayment can happen on a monthly basis, obviously that will have impact on the notional. So that's basically what we see. Of course, you have to make it more practical. So you have to make some adjustments to make it this accruing period I have mentioned before. So to make those functions aligned. Okay, so here we have the bullet. we had now irrational behavior. So now let's switch to, again, maybe rational first. Rational, and we look at the annuity. So annuity is also, it's a very interesting graph. So here, this is still the rational setting. So it's only, okay, 0, 1. It's very much digital because there is a 0 incentive. And then after some point, it will be only switched to 4% incentive. So you see, of course, this incentive of prepayment, it's also important factor that plays a role how we choose this maximum prepayment that clients decide. This could be, for example, also limited by the law. So how much money can client prepay? That could be a constraint that is imposed on the mortgage. Otherwise, there could be some additional penalty that would stop clients to do the prepayment. That's also something that can exist and actually exists in practice. So this is, again, the distribution of a swap. You see here the red line, this is essentially there is no prepayment profile. So everything is just client is paying according to the schedule. And the part where we have below is the part where we have this additional risk, uncertainty of annuity. It looks very, very much organized. Let me try to maybe make, give me 3 paths. Let's see how this looks like. So you see there's some irregularities, and now this number of paths increases. We see clearly that there is some pattern. But of course, if you look at only 3 paths, that's not really the case. So it's also those are kind of the most important, I would say, takeaway here is that comparison between bullet mortgage and annuity is that this uncertainty that we have here is strongly depends on the schedule that client receives to perform his repayment of his outstanding notional. So bigger the notional client will repay, then this will have a lower impact on our. So as we go in time, there's a less and less notional to be prepaid. And of course, that will mean that there's a reduced volatility, reduced uncertainty of those notional profiles. If there is a case of a bullet, I think this is the worst case scenario where we have notional that does not decrease in time, then we have the biggest risk from prepayment perspective. And here, maybe the last step, let's go back maybe to this 100 paths for the notional, and here we would just do irrational. Irrational cause. So here again, to some extent, it's similar to the bullet case, but here we also see that there's those paths, they just decaying exponentially to 0, and there is a huge difference between if we don't prepay and we prepay. So there is this area here. It's not optimal at all for the client to do any prepayments. And of course, that has to do with this incentive function that we have specified. If you play in this code, you will see that there is different shapes you can receive of this. You can see from this function. It could be also that there will be like before we have. If you have this rational behavior, that will be very close to the red line. Otherwise, it's not close. But depending on the profiles of those two incentive functions, you may see completely different shapes of those notional schedules, stochasticity of the notionals. In this block, we will discuss the relation between mortgage portfolio, index amortizing swap, and possibility of decomposing this complicated rather portfolio, which consists of rather involved stochastic processes for the notional. We will show how to decompose this portfolio into part which is linear, so this will be amortizing swap, and also part which is non-linear, which is part corresponding to the volatility component of swaptions. So it will be a very illustrative case, which will show you that if you would like to price mortgage portfolio or hedge mortgage portfolio, you don't need to necessarily go to the index amortizing swap case, so you don't need to buy an over-the-counter this derivative, but we can also, from the financial engineering perspective, you can decompose this complicated payoff into parts that you can simply buy in the market. So in this case, will be amortizing swap, so the notional which is amortizing in time, and also the part which is non-linear and is handled by pricing of swaptions or florets, couplets. Of course, this is in simplified case. This will be only floret or couplet. So here in this experiment, this derivation, simplified derivations, we consider only 2 periods. This is just to show you the main concepts. So we see we have a summation from I equal to 1 to 2, so from 1 and 2. And then we, in this case, if I is equal to 1, we see that it will be empty 1. Then the LIBOR is already at time t0, so it's known today. And also the notional, the mortgage at time t0 is also known. So this part would be the payment C1, which is fully deterministic. There's no prepayment impact. On the other hand, if we go to the second case of the payment at time t2, then this, if we have I equal to 2, then we see that this notional becomes nt1. Then we have a discounting from m at t2. And then this LIBOR part, because this is the float part, so to be t1, of course, t1 and t2. This is what we see here. And of course, if we have the simplified case only with 2 periods, and then the last part, then the LIBOR at time t1 is simply a swap at time t1 with a one payment time t2. So this is nicely collapses. So the swap evaluation collapses to pricing of this will be a LIBOR rate. And okay, so if we have this kind of simplified case, our notional will have two states. So this is the also second simplification. We don't consider the whole distribution of all the possible outcomes, but we will assume that we will have only two outcomes. Whether we, in this case, end up, this means that the LIBOR rate is higher than the strike. This means that there is no prepayment. And then we have a second part where we have an indicator when the new rate, the swap rate or LIBOR rate in this case, would be lower than our current. Then we do the prepayment, then the notional would decrease. Now we have some summations of indicator functions. So if we start from this side, what we can do is that we see that n up can be written as n up. And then we have indicator k smaller than L plus n up. And then we have indicator k less than equal, which this is continuous case, so we can forget this with L here. L here. So then if we have this decomposition, then we know that n up 1k smaller than L, this is this part, would be equal of n up, and then we have this one we take to the other side. With other side it would be to write this way. Then we end up with that n up indicator k smaller than L will be equal to n up, and then we have a minus n up, and then we have indicator of k smaller than L. And then if we substitute those terms, this is what we have. So this is typically what we do if we, this kind of expressions, we can always add and subtract the same quantity. This is what we end up with. So we see that the notional at time t1 consists of two elements. We have n up, and also we have this difference of n up minus n low. So the difference of the possible outcomes in the future of our notionals. And then this will only be positive, this part, if strike is bigger than LK. So this means that only if the prepayment will take place. So you see, if the prepayment wouldn't take place, this will be just 0. So then our notional that our mortgage has only would stay on n up. And of course, if we prepay, the mortgage decreases, that will be handled by this part. So this is actually, at this point, you can already see that there is some kind of a linear part, so n up. And then we have a notional, which is handled also with this indicator function, which is nonlinear because we have this nonlinear effect. And this is also nicely corresponds to also the part of a call option. And that this will be clear in a few seconds. So if we look at this payment, the second payment, because we have a summation of in this portfolio or in this swap, the index amortizing swap, we have a summation of two payments. The first one is deterministic, is trivial, and the second one it is here. So then we have this C2 is of course the discounted MT2 MT1, and this MT1 we already established what are the possible outcomes. And here we have, of course, accruing period and K minus LT1. So if we just substitute for this NT1, this expression that we have here, so this will be substitution, and this is what we have here. So we have an N up in this case, and then have a minus and then we have n up minus n low, and then we have k minus, this is k minus L, and then we still have this is important, we have this plus, because this value will be always only positive, or if we have this condition, so k bigger than L T1, so of course this quantity has to be positive, otherwise it will be zero. But this is just a different way of writing the indicator function that we have here. So this one, again, you see this one is deterministic because we have n up. So this one can easily price using just the linear derivations. So this will be a discounting of the LIBOR from time t2 until t0. And then we have here an option, which also depends on this notion. So this is what we have here. So this pricing, of course, since we have determined what are the possible outcomes for those notionals, we have this part. This will be our the part corresponding to the n up, and then we have this optionality part, which is the floorlet, because if we see it's a floorlet because it's a k minus, couplet would be L minus k, so it's a floorlet, and then we have a multiplication of the difference of the possible outcomes for notional up and down. So this means that index amortizing swap is actually consists of two elements. We have this term C1. So the C1, actually, it is a term which is here, the fully deterministic part. And then we have term C2 that we have just derived here. And if we look here, it's actually the C1 part you can consider to be amortizing swap, because that part is a purely deterministic. And then we have a second part which comes from this non-linearity, and this will be a floorlet. In practice, that if we have a realistic case where we have not only two payments, this kind of index amortizing swap, we can, the profile of index amortizing swap, we could mimic using a proper combination of swaptions or maybe couplets and floorlets. So then the risk profile would be preserved. Some takeaways. So the first one, the price here redefines the index amortizing swap as a combination of amortizing swap. So this is what we see here, and the floorlet. This is a very important, also an interesting insight, because it enables us to separate a linear component from a non-linear one, suggesting that the long position in swaps plus a short position in option on the refinancing driver better replicates the IS. So here we see that if there will be no prepayments, we have only amortizing swap. This is what we also have seen before. And then if we have prepayments, then some cost involved, and this cost in this case will be a floorlet, so optionality part that client has to prepay. And the second important takeaway, purchasing a mortgage can thus be seen as entering a long position in a swap, while the prepayments effectively reduce the notional of the mortgage. Thus the option to prepay would equal an option to enter a swap. Actually, in this case, would be also swaption. So this is kind of a very nice and simplified case, but also very importantly illustrating here how this decomposition of index amortizing swap can be done. Of course, in practice, it's never so beautiful that we can simply derive it on a paper. You will need to do some kind of optimization that you can replicate the risks profiles. So, for example, you will need to look at the delta, of course, Vega and other Greeks in order to find this kind of profile matching from your, let's say, simplified instruments to your index amortizing swap. But this is also what we have already discussed in previous course and this course, that in the market, if we have an exotic derivative, this derivative could be hedged or also replicated, typically by simplified or liquid instruments available in the market. This is also present here. We have advanced exotic derivative, which is index amortizing swap, and we show we are able to replicate its behavior by combination of linear products. So that will be biggest part of our portfolio will be amortizing swap. So this is liquid, available easily on the market. And we have non-linear part, which is more expensive, but also potentially it's a risk that bank preferably would like to hedge. In this lecture, we have focused a lot about the prepayment risks and impact of prepayments on the type of amortizing, the notional of the mortgage portfolio that we will obtain. And of course, this was kind of extensive study. And however, we also have additional type of risk that it's also present in the mortgages, especially in European mortgages or Dutch type of mortgages. And that risk, especially from perspective of a bank, is associated with possibility of the client to choose the rate, the fixing rate of the mortgage. So how does it work? So we have two dates. Essentially, we have a date T0, which is the quotation day. This is the date when a client would decide that he would like to have a mortgage. Then bank would give him a quote. And then we have a second time, T1. This is the time, which is the period when the moment when a client will sign a contract with a bank. And of course, between those two dates, so if we have a time here, this is today here, small t0. Actually, here we can make a t0. So today, if there's a client coming to a bank and asking for a rate for his mortgage, then he will get the rate as seen today. So this will be the rate of a swap from this will be t0 and then until the maturity of the last payment of the mortgage, observe at time t0. And then we have, so this is this rate that you will see today. However, there is a period until T1 when the contractual part takes place, when client signs the contract with a bank. And then, of course, here we have a different rate. This rate will be S, and here we have a T1 TM, observe at time T1. And by Dutch law or in many other European countries, clients may choose actually if the time T1 when the signing takes place, clients may choose whether he would like to have, of course, the rate, the lower rate of the two. So this means that if at the signing part, the swap rate is lower than at the period of quoting, then client may choose, of course, this is reasonable to do, to take the lowest of the two. However, again, from perspective of the bank, of other mortgage issuer, this represents a potential risk that has to be handled and has to be hedged. Of course, this is also the function of time. So if this period will be very short, let's say a few days, this risk will be very insignificant. However, in practice, this could last from 1 up to 3 months. Imagine there is a period when bank needs to also check the background of the client, whether there is enough financing, whether all the paperwork is handled. And signing the contract basically means this is the moment when two parties agreed about future payments. But before it takes place, of course, mortgages are very expensive. So there's not a few euros. Typically, we're talking about buying houses. Then we talk about hundreds of thousands of euros, sometimes maybe millions. So this takes quite some time for financial institution to make proper checks whether the property exists, whether the property is of good state, whether the value which is quoted or the mortgage that is asked covers, actually, it corresponds to the value that is assessed by the third party. So you can imagine this is the whole process that takes quite some time and can actually take a few months. And of course, in reality, swap rates market is alive, so it's continuously moving. This means that there is a fluctuation, there's risks associated with this swap rate movements. And of course, even if it's a few basis points movement, if you have a mortgage of 1 million or even higher mortgages, those are significant amounts that would translate to your monthly payments. So this is not a peanut that you could simply forget. This is kind of relevant. And especially if you talk about a portfolio of mortgages, this is substantial risk. And if bank does not handle this type of risk properly, this part will be consumed from its profits. So this is important to manage properly. Okay, and the risk so this type of risk, when a client can choose between the quotation date and also the signing date, the rate, that's called pipeline risk. This is the name associated with this risk. So the definition here, the pipeline risk can be characterized by the risk that the interest rates increase over a short period. And of course, client will always choose one way. So if this rate here at time T1 would be higher than the one at the quotation, client would like to stick the one which was quoted initially. And if this rate at time T1 would be lower, then of course client would like to choose the one which is the lowest. So you see that if we choose between the highest and the lowest, we typically deal with kind of optionality. So this will be also related to some way to the previous block when we discussed of an index amortizing swap, which was very simplified case. And this, you will see the same kind of methodology, the same kind of strategy would be applied in assessment of the pipeline risk. And the main challenge for the pipeline risk is that that is hedged using swaptions. So this is the remember in index amortizing swaps where we were doing the hedging, and we had a very simplified case where we did the hedging with floorlets in a proper swap case. So instead of only single two periods that we had, then we will need to deal with swaptions. And the same is here. But this also implies that we can only hedge the current pipeline risk. As new mortgages enter the pipeline, one needs to adjust our hedge. This means that essentially, if bank performs the hedging, it doesn't look like a scenario where we have 10,000 clients coming one day and everyone is getting a mortgage. There's a continuous process where there is a portfolio of mortgages which is live, and then we have a new mortgage which is added on the top. So this means that there is a pipeline and there is a new risks which are continuously added to the portfolio. So suppose you have a mortgage portfolio with 10,000 mortgages, there's a new client coming, and of course, before client came, you already performed the hedging of the existing mortgages. So there is a new client coming and there is a new additional risk profile change that you have to adjust. This means that the process of hedging these type of risks and also prepayment risks, it's a continuous and requires continuous recalculation of values and associated profile risks. So this is ongoing process. This is not something that you will just do it once, client. Actually, you have to do it per client, but this means that those risks are accumulated in a portfolio. Concept of portfolio, of course, we already discussed that because we deal with swaps, and those are the instruments which require rather large notionals. This means also mortgages need to be bundled together in a big portfolio of mortgages, and then we talk about hedging of those portfolios. So let's take a look from the mathematical perspective how to arrive at this, actually, how to price pipeline risk. So first we have two dates. So in the previous slide, we had T0 and T1. So we have a TQ, which would be the quotation date. And then we have the signing date or the settlement date, TS. And we have basically two rates that we could receive from a bank. So this will be the rate from TS, the settlement date, until the maturity of the mortgage, as seen at time TQ. And then the second swap rate will be TS. So this is the same from the, so you see these two mortgages, this swap rate and swap rate, they are seen over the same period of time. So this is the lifetime of the mortgage. However, they are observed at different periods of time. So one is observed at time TQ, the quotation, and then this one observed at time the settlement. So this is the moment where we sign the contract. So if we just put them together, because essentially we need to incorporate this optionality for the client. So client will choose the rate at the quotation date. If the swap rate will be smaller at that date, will be smaller than the rate at the settlement date. On the other hand, we have plus, because as we deal with the indicator function, we can say that the rate that client would like to have for his mortgage would be the one from the settlement and the settlement date, if the settlement rate will be smaller than the one on the quotation. What we can also do here, so we have this TS, we can add and subtract. So you see we take this kappa TS, we add and subtract kappa TQ. So this is just, you see it cancels out. This is just equivalent. But this allows us that we have this STQ smaller than STS. And then we have other side. So this means that we can actually put this part together. Actually, this will be this part. No, so we have to take TQ. So this will be this one. We will take, and then we glue it with this element here. So this is what I will do here. So we take this part with this indicator function. We move to this expression here, to this element. We have them together. And you see now, because we have S smaller TQ or STQ smaller than STS, and then on the other side we have STQ bigger or equal STS. So this essentially equals to kappa TQ. And on the other side, here on the remainder, is the difference between the settlement date, her swap rate at the settlement date, and at the quoting date. And then we have this indicator function. So you see that we end up with something very similar as we have seen also for the single index amortizing swap when we talk about the setting up the hedge for index amortizing swap. So we have a part where we see, okay, if there is a client coming for the mortgage, the rate will be the quotation rate and the quotation period. And then we have optionality part, which corresponds to the difference of the swap rates between observe at time TS and observe at time TQ. And then this only will be positive, only this rate will be positive only if the STQ will be bigger equal STS. So this is the decomposition. So we, in the case of index amortizing swap, we decompose index amortizing swap to the part where we have the amortizing swap, so very linear product, and then the other remainder was swaption, and the same type of strategy and the same kind of output we have in this case. This is typically what we do in finance. If we have some exotic derivative or some structure which involves some kind of optionality, first, what you would like to do as a structurer, you would decompose the derivative into elements which are linear. This means those are typically the most liquid, the easy to handle because they don't require volatilities. So there is no vega hedging, etc. And then the remainder part corresponds to the optionality, which is much more involved and often much more expensive. So this is this part. Okay, so if we take this, if we collect this indicator function, we can also represent as the maximum. So this is equivalent. And then, of course, at the end, we would like to price the contract. So we would like to price the quotation date. So we because at the end, we would like to see how much at the time TQ, what is the price of optionality for the client to that he has optionality to choose or switch between the rates. So this is the rate the value that we need to assess at time TQ, because potentially this value would need to be added at the quotation price to compensate for this additional risk. So this is what we do here. But of course, here you see it's a swap at time TQ, and then we observe it at time TQ. So the filtration is TQ. So this part will be only kappa TQ, and then the only part which is left is this. So this is what we have here. So the value of our contract would be kappa TQ. So there will be a swap rate, and then we have a minus, and then we have a maximum kappa TQ minus kappa TS, and then we discount it from TS. So this part, you can see this is a constant, it's a fixed, because it's known at time TQ. However, this part, because TS is after time TQ, this is unknown. So of course, this represents optionality. And of course, those kappas, essentially, those are just swap rates. So the whole contract here on the right-hand side represents swaption. And of course, the easiest way to handle this type of risk is by using Black's formula. So this is something we already discussed in this course. So you can just assume shifted log normal distribution process for the swap rate, and then you can simply assess this expectation. Of course, problematic part will be if you have multiple of those, then you have to really take care of proper hedges. But this is type of a European option you can think of. So then what you need only volatility for the swaption with those configurations. So we have a TS from the settlement until the maturity, the end of the mortgage. So this is the underlying. And the zeta here, this is the premium that we are looking at. But you see that actually because we have this minus sign here, and assume the zeta in both cases will be the same, it will nicely cancel out. So then we have only the difference between a strike or a swap rate at time TQ, or the quotation date, minus swap rate at time settlement. So this is obviously a swaption. And that's basically how it should be priced. Now is the time to summarize the lecture about mortgages. It is one of the most the longest lectures in this course. However, I hope that you have learned also about this aspect of financial engineering when you don't only deal with, let's say, pricing and the risk neutral world, but also need to take information about the client's behavior and their incentives. This is the purpose of this lecture. I really think that this is potentially, it can also give you direction of research and also studies. Okay, this lecture consists of many points. So we started this lecture with a different type of mortgages. We have discussed bullet mortgage and also annuity mortgage. I hope you understand the difference. Basically, it's a huge difference. So, because we started with the bullet mortgage because it's one of the simplest mortgages, where we have only one payment of the notional which takes place at the end of the contract, while there is no repayments. However, client may still do prepayments, which is the part that we focused extensively. In annuity mortgage, we always, every monthly payment is the same. This is the most important takeaway. And we do some kind of repayments. This means that outstanding notional decreases in time. In both cases, we have also discussed some Python experiments where we can generate a payment schedule of the mortgage. Then important part was about prepayments and what are determinants for the clients to perform prepayments, because this is also this is super important because clients may behave depending on different refinancing incentives. So some people may be, for example, looking at the swap rate. Some people may have other factors. Here in this lecture, we concentrated only on, let's say, observables, the directly linked variable to the market, which was actually looking at the swap rate. However, in reality, these incentives would be much more advanced, would be much more complicated, as people will not only decide about the mortgage based on the market circumstances, but also about the overall economy, their taxations, savings account, the rate on the savings account, and so on. So this is, let's say, the research topic on its own. Then we went to and let's say this was, I think, around block number 3, when we concentrated on linking the mortgage, pricing of mortgage, and also inclusion of a refinancing incentive, and that was linked to index amortizing swap. This was the place where we connected D2, and then we noticed that this kind of combination nicely fits to the over-the-counter derivative, which is the index amortizing swap. And that was basically done by also inclusion of the refinancing incentive into this the swap. And then the last part, we had done some experiments, numerical experiments, where simulation of the notionals depending on stochasticity of prepayments was discussed. And this was done in this part, which is also very, very important, because this actually shows you what are the possible trajectories of the notional depending on stochasticity of the market, and also the incentive of the client to do prepayments or not to do prepayments. And then we have linked that on a very, let's say, simplistic case to pricing of swaptions. So this index amortizing swap can be associated with pricing of swaptions. So typically, as I already have mentioned in this course, the objective in financial world is that if we have a complicated contract, we always try to decompose this contract into building blocks or contracts that are much simpler and available in the market. And that way we can hedge all the risks or most of the associated risks of the complicated contract. Finally, there was a discussion about the pipeline risk. So maybe you remember, this was very much linked to the step that we have done here, the transition from index amortizing swap to the pricing of the stochastic prepayment and swaptions, and the same kind of strategy, the same kind of result we have obtained once our clients have possibility to choose the rate at the quotation date or at the settlement date of the mortgage. So this is also very important from the banks and management perspective. Now is the time to summarize. So we summarize the lecture and the homework. Today I have prepared 3 exercises. The first exercise is related to slide number 35, where I have shown you how to perform this simulation of the notional, which will depend on the type of a mortgage and also type of so the mortgage and also incentive function. So your task, so this part I have done for you. Now your task is to basically perform the pricing of this contract. And so essentially what we have to do is to implement MTI and also LIBOR and then evaluate this expectation. So it's a little bit of programming today. And then you have to discuss different impact. So the impact of the value depending on whether client behaves irrationally, and then different incentive functions. If you can play with that, will be also important. Second part is about convexity. So maybe you remember in the lecture I have discussed that if we have a LIBOR, so we know that the LIBOR would be a martingale under its own payment measure. However, if we have a function with square or we have other function of the LIBOR, then we cannot simply have equality here. So this is inequality. However, what we can also do, we could say, okay, we have this expectation and we say this is equal to some as it would be a martingale. So this would be equal to the LIBOR squared at T0. So this is exactly the same T0. Plus we have some correction term. So this is your task. So first, you have to essentially find out what is this psi such that this would be equality. And this is what you can do with either analytically or numerically. So this is, we'll leave it to you. And of course, here the task would be you need to define some kind of a process for LIBOR. I think I showed you already how to do it. And then you have to simulate this expectation and then find out what is this psi depending such that these two left-hand side and right-hand side would be equal. And then just to give you a little bit of feedback, later in this course, we also discuss the concept of convexity, and this will be this kind of effect that we will observe. So typically in finance, when people have this kind of expectation, they will just immediately try to approximate by this kind of term. However, there is some extra reminder, and that reminder is called convexity correction. And this is the task of today's exercise. So it would be good if you could analyze that with respect to different times. So the Ti minus T, so actually this is Tk minus 1, and then also different volatility values, and then we will see how big impact is depending on those two factors. And then the final task of today's lecture is to look at the slide number 17, so the part where I have introduced the scheduled payment for annuity mortgage. And then what we will do, your task is that you have to make sure that the prepayments, not because right now the code is made that we have a prepayment rate. This means that every month we do some prepayments. Your task is to change this code such that the prepayments will only happen few times in the lifetime of the contract. So we have to do some, instead of rate, we have to do some amount payment. So this will be also a programming exercise. I hope you enjoyed. I think those exercises, I chose them such that you will get more insight of pricing of mortgages. And I think also they will give you nice introduction to follow-up lectures when we talk about convexity. And also, of course, you will do some Python coding, which is always a lot of fun. See you next time.